Yes, nice. Diciamo
c'est quelque chose de plus détaillé de toute façon pour moi. C'est
okay, so when those on that's this one button. So that's used. Oh, it's talking here.
Ah.
This one is back.
Okay, thank you.
I just imagine. Yes, yes.
Yeah.
Oh, nice.
Well, now it's time to begin for today. And the first talk will be by Lucian Badescu on infinitesimal extension of rank 2 vector bundles on submanifold of small codimensions.
Thank you. First of all, I want to thank the organizers for inviting me here. It's an honor for me, and especially because the celebrated person is Zach. He met us, especially, if I remember well, especially in the 90s in Italy, a couple of times. And of course, about his influence of its mathematical work was absolutely well known everywhere. Okay, so roughly speaking, the problem is such a problem was already considered by Grothendieck in his algebraic geometry seminar, Séminaire de géométrie algébrique, 6061. The setup is as following. X is a submanifold of a complex projective manifold P of dimension, say, capital N, and X is of dimension small n. First of all, some well-known definitions. for every non-negative integer I, we denote by x of I the i's infinitesimal neighborhood of x in P. This is nothing else than the subscheme of P, whose sheaf of ideals is I of x. This is the ideal sheaf defining x. I plus 1 raised to the power I plus 1. Of course, when I is 0, we get nothing else than x itself. Okay, so the problem also already studied by Rothendick in 60-61 is one of the problems, was called somehow obstruction, some obstruction theory. If E is a vector bundle of some rank R on say i's infinitesimal neighborhood of x in P, so a natural problem is to give criteria for extendability of E to the next infinitesimal neighborhood, x of I plus 1. And under the above hypothesis and notation, one of the results proved by Grothendieck was the following. Under this assumption, this is the I plus 1 symmetric power of the normal bundle of x in P. If this cohomology group is 0, then E, our vector bundle, can be extended to the next infinitesimal neighborhood as a vector bundle. Of course, in particular, if this group, the homology group, is 0, this problem is automatically, the answer to this problem is automatically positive. In particular, this holds if x is a curve. This condition is automatically fulfilled. But what we are trying to say something is connected with the case when x is of greater dimension. Actually, we are going to assume that x, first of all, P is a projective, is a complex projective space of dimension capital N, and X is a submanifold, complex manifold of P of dimension, as I said, little n. Okay. And our hypothesis, our first result, will say something about the problem is we are trying to understand this condition somehow more geometrically, because the obstruction for extending the vector bundle on X, say, to the first infinitesimal neighborhood is, it's a problem which appears quite often in algebraic geometry. In particular, okay, let me finish this last sentence. If, moreover, we have this vanishing of H1 of the same sheaf equal to 0, then this criterion tells us that the extension is given unique up to isomorphism. Well, actually, the obstruction for extending a given vector bundle from X to P to x of 1 lies in some cohomology class of ZH2 that appeared before. But we know absolutely nothing about that cohomology class in an explicit way. So our first problem in this paper was to understand somehow from a more geometric proof, from a more geometrical, more geometrically, this kind of extensions. And as far as this problem, this first problem studied in this paper is concerned, okay, we shall assume, as we will see in a minute, that X is of small codimension in our capital N dimensional projective space. I'm going to be more precise in a minute. Okay. So first, maybe it's better to start with some historical motivation by mentioning the following very nice result. This is a very nice application of some theories. This result is very geometric, very concrete. Is due to Griffiths and Harris, was proved one of 1983. Harris and Bullock gave somehow a different proof, and 2 years after, 4 authors, one of them is here is the chairman of this. Okay, Lucian Badescu, okay, gave a completely different proof, much shorter and much more in the spirit of Grothendieck's algebraic geometry seminar. The result is as follows. X is a smooth projective complex surface embedded in Pn, with n at least 3 as a complete intersection. Then let y be a smooth connected curve in X such that this canonical exact sequence of vector bundles splits. Then, under this hypothesis, there exists a hypersurface H in Pn such that this equality holds, where this intersection is in the scheme theoretic sense. So, scheme theoretically, why is this intersection? And why I recall this result, especially from the point of view of the proof of Lucian Badescu's theorem, because one of the, first of all, the condition of splitting like this appears in the proof, but not only. One of the main steps in their proof is to extend a line bundle, namely the restriction of all x of 1, to extend the normal bundle of y in x to the first infinitesimal neighborhood. So this is an example which shows one of the most, it's the rank of the vector bundle is 1 in this case. So Griffiths, Harris, Hewlett, and so on, used as a method of proof the variation of the Hodge structures. Instead, as I said, a very elegant proof of elliptic Lucian Badescu, very short, but a very, very, I would say, clever proof, an elegant proof. Was much I liked it because it was somehow according to my taste. The idea to get the extension of the normal bundle of the curve y on x to the line bundle on x, the very first step is to extend it to the first infinitesimal neighborhood as a line bundle. And this step is absolutely crucial because, as these four authors show, somehow in this context, it's enough to do it to extend to the first infinitesimal neighborhood, our line bundle, in order to have it in general under this very special hypothesis, of course. Now, more generally, a first observation is the following. We have a submanifold of Pn of dimension small n, and E a vector bundle of rank R in this range. With R greater than 1, greater than or equal to 1, and smaller than or equal to n minus 1. And we may consider the following condition regarding this triple. The condition is the following. Okay, under this hypothesis, there exists an integer, large integer, L0, such that for every L bigger than or equal to L0, there exists a section in this E of L whose zero locus is an R codimensional submanifold of X, is smooth, and maybe I didn't know. Okay, is smooth, and such. So we can consider this normal bundle sequence such that this sequence splits. It's enough to have in this condition for any L just one section satisfying this condition. And a simple proposition, very easy to prove, is the following. Under these conditions, if there exists, we assume that this extension exists to the first infinitesimal neighborhood, then there exists an L naught such that for every L bigger than or equal to L naught is something like the above condition, which I'm going to say, such that this time for every section, global section of this vector bundle whose zero locus is smooth and R codimension, the exact sequence above of normal bundles splits. This is it. Okay. In particular, the proof of this proposition is rather straightforward. But I mentioned it because the first result of this paper is a kind of converse of this proposition in the special case when the rank of the vector bundle is 2 and when X is of small codimension in Pn, in the sense that will become precise in a moment. Okay. I skip the proof of the proposition because it is, as I said, it is completely straightforward. Maybe the last point is not completely trivial, because this proposition, this proof, to get the splitting of the vector bundle, we have to use somehow an elementary but a key lemma, which was used also in the paper by Lucian Badescu Stroine. So, to understand what I'm going to say, the key lemma I was talking about is the following. In this situation where P is an arbitrary projective manifold, X a submanifold, Y a submanifold of X. Y at least of dimension 1. Then, in this condition, this exact sequence splits if and only if there exists a closed subscheme Y prime of the first infinitesimal neighborhood of X of 1 which is a local complete intersection in X of 1 of codimension exactly the codimension of X and Y in Y, and such that we have this equality scheme theoretical. In the paper I mentioned several times by Lucian Badescu, Lucian Badescu Stroine, they needed this lemma in codimension 1. But the generalized lemma, the lemma can be generalized to the case where the codimension is arbitrary. Okay. So I need the condition. Excuse me. Okay. The lemma is here, and the end of, as I said, the crucial condition we want to impose, otherwise such a statement doesn't say anything, is that Y prime, this extension of Y in the first infinitesimal neighborhood, should be a local complete intersection in the first infinitesimal neighborhood. Okay, this proof was, one proof of this generalized lemma can be found in the PhD thesis of one of my former PhD students, which was used for some reasons. Okay, so the first theorem is the following. First result. X is a submanifold in Pn of dimension small n, such that n is bigger than
equal to n plus 3 half. This, by this inequality, I understood the small codimension in this theorem. So E is a rank 2 vector bundle on X, which satisfies the above condition I talked about, just talked about. So E can be extended uniquely up to isomorphism to a vector bundle script E of rank 2 on the first infinitesimal neighborhood of x in Pn. I have to emphasize under this condition. Okay.
What is the condition?
Complete condition.
The existence of section such that,
Okay.
like, there was for a large enough.
This one, start.
Yes.
Start. So maybe it's better to repeat it. E is given. It's an arbitrary vector bundle of rank R. So we consider this exact sequence where Y is the zero locus of some section. With this S is actually this SL. I forgot to put SL script. Such that this exact sequence splits. This is the condition, which, the hypothesis in the theorem. From this point of view, theorem 1 is a sort of converse of the proposition I stated above. I mean, if we have this condition, then that our rank 2 vector bundle can be uniquely extended to a vector bundle on the first infinitesimal neighborhood. I mean, somehow, in this case, this condition is necessary and sufficient in this case, in this special case. If I shall have some time at the end, I shall indicate some, give some hints about the proof of this theorem. One of the ingredients is a generalized version of well-known result, which allows us to construct rank 2 vector bundles. Probably it's folklore, absolutely folklore, but I didn't have a reference for this result in this generality. X is an irreducible, not necessarily reduced, algebraic scheme over a field, and Y prime is a local complete intersection subscript of X of codimension 2, such that the norm, in this case, we can consider this normal bundle, which is of rank 2. If we take the determinant, this determinant, we assume that extends to a line bundle L on X, such that this condition holds. Then the conclusion is that we can get an extension, script E, of our vector bundle E we started with, such that the determinant of E is isomorphic to L, and its zero locus is precisely Y prime as a scheme. Okay, this equality is scheme theoretical. If furthermore H1 of X and L dual is 0, this extension is also unique. Probably the experts would say that this result is. I included a proof because I didn't have any reference of this theorem in this generality. Now, I say nothing now about the proof of this theorem, but let me give some examples of interesting examples of submanifolds of Pn, which are of small codimension in the sense that inequality holds, the inequality appearing in the theorem, in theorem 1. Okay. Start with the Grassmann variety of lines in Pn, where n is at least 3. In other words, this is not a projective space, a projective space. And take the Blücher invading and denote by x prime of m the image. So in the book of Harris, Joe Harris, one exercise asks to prove that this variety, this subvariety of this projective space is 4-defective subvariety of this projective space. Meaning exactly that there exists a linear projection from this space to this one of a center, a linear subspace Ln of this dimension, precisely, which does not intersect x prime n, and such that the restriction, this restriction is an isomorphism, a biregular map. Okay, in this case we get the image we get is a submanifold of this projective space where this number is our n capital and the dimension of the Grassmannian satisfies precisely, is equally precisely this capital N plus 3 half. So at least the theorem state, the first theorem stated applies to this situation. Now, I want to speak about present the second result of this paper. Consider this Grassmann, general Grassmann variety, which is not a projective space. In other words, it satisfies, we have these inequalities. On this Grassmann variety, we have the universal quotient bundle. Fix an arbitrary projecting embedding in some projective space. Not necessarily this one, not necessarily the Blücher embedding. Okay? And we have this result. Under the above notation and hypothesis, the universal quotient vector bundle E of this variety with K satisfying this inequality cannot be extended to a vector bundle on the first infinitesimal neighborhood of X in Pn. maybe I should insist a bit give some hints about the proof of this theorem. The proof is not completely trivial. It's not, I would say. Okay. Okay. Assume, by way of contradiction, that there exists a vector bundle E, an extension of script E on X of 1 such that this isomorphism holds. So, we have this XX sequence, and after tessoring it by E, we get this XX sequence. And assume for the moment that we have this vanishing. Okay, then from this hypothesis, we can deduce that this restriction map is subjective, because that H1 vanishes. And if we consider the natural quotient, universal quotient bundle, in particular, we can lift. We know the dimension of this one, of this space, and okay, take a basis of this space, and we can lift these spaces, the elements of these spaces here. Since phi is subjective, these sections generate E, and hence, by Nakayama's lemma, these sections also generate script E. In other words, we get such a subjection. Then, by the universal property of the Grassmann variety, we get a morphism from this scheme to X, which actually is a retraction of the embedding of X in the first infinitesimal neighborhood. But this is already a contradiction, because this condition, considering the embedding of X in X of 1, admits such a retraction, an old result of Van de Ven tells us that X should be a linear space. And this fact was excluded by our hypothesis, because X is not isomorphic to a projective space. So, try to see, to better understand this vanishing. Okay. So the equality 5 was the vanishing of the dual of H1 of the dual normal bundle. We claim that vector space H1 of appearing in the previous condition, this space is isomorphic to this one. So in order to...
And what is lambda? What is F?
Okay, I'm going to... So we have this diagram. this canonical diagram. And F is nothing than the co-kernel of phi of this map. And actually, up to a twist, this F is the sheaf of principal parts of O x of 1 twisted by 1, by O of 1. That is F, because it's absolutely crucial to understand this. I hope the rest of, so we transfer this diagram by E, and we get this commutative diagram. It's exact rows and columns. So, the second row of this diagram is the following XX sequence. We try to understand this space. So in this cohomology sequence, the first and the last term vanishes. This is not a completely not a trivial result. It's a vanishing coming, which can be proved as an application of node vanishing, some vanishings for Grassmann variety and more generally for the Fleck manifolds, proved by George Kempf. Okay, so this space is isomorphic to this one, modulo these two vanishings. The vanishings of this, the first and the last term. Okay, so all we have to do is to show that this guy is 0. Because we assumed that the universal quotient of the Grassmann variety, which is not, of a Grassmann variety, which is not a projective space, that vector bundle can be extended to the first infinitesimal neighborhood of our X in P capital N. For some time, I didn't know how to prove. Actually, I didn't. Fortunately, last year I found out that this vanishing is a special case of a result, much more general vanishing result, proved by Giorgio Ottaviani and somebody else. Okay, I have also the references now. And it is not, I mean, the method of proofs requires representation theory. Maybe there are some, since there are some experts here, maybe could tell or knows how to prove this vanishing directly. But I tried to do it. I thought about this problem for a long time, and after some time I asked, when I met Giorgio Ottaviani, who is the expert in representation theory, maybe in Italy, right? Yeah. Show me that this vanishing holds always. He also told me that proof directly this vanishing is not necessarily easier than proving the general result. Okay, so I have still 8 minutes. Maybe I can tell.
Does it work in arbitrary characteristic, or this is the
No,
point?
no.
So exactly this is the
No,
point where you need
no, only in characteristic 0, because.
But Kempf vanishing.
No.
Yes, in positive characteristics.
Maybe the second result, yes, holds in arbitrary
Yes,
characteristics.
this
Yeah,
result.
yeah.
So Tobiani's thing also works.
Only the second result. The first one, no, because I wanted to say something about the proof of the first result. Okay, so the idea here is to understand the following diagram. So we come back to the frame and to the proof of the first result. We have this y prime. No, here is x. Here is y prime, and here is it's completely easy to prove that this first mapping is an isomorphism. Also, that beta is an isomorphism. For this, we have to use the Kodaira-Le vanishing. Here, the main, okay, so it's isomorphism. This is injective because this is an isomorphism. So it's enough to prove that gamma is injective in order to deduce that all these maps are isomorphisms. And isomorphisms. But, okay. So, recall that we assumed that that normal bundle sequence was split. So we have to prove that we can the extension of our vector bundle. We are working in those conditions, so it makes sense to consider this. I mean, when the key lemma in this case tells us that the existence so x of 1 so y prime intersected with x is still theoretically y. Okay, so I'm not going to enter into details, but applying another couple of times, again, Kodaira-vanishing, Kodaira-Le theorem, some, for instance, in this case, we have this embedding. The Schiff ideals of y in y prime is square 0, so we can it makes sense to write the following exact sequence y prime here, or y prime star. This is the sheaf of nowhere vanishing functions on y prime functions, then y, and the h1 of this guy vanishes. And some repeated applications of the key lemma, the vanishing theorem of Kodaira-Le this sequence, exact sequence, is the truncated exponential sequence associated to y in y prime. Repeat, it makes sense to consider this because y, the idea of y in y prime is squared 0. But unfortunately, so maybe I was not clever enough to how to arrange this talk. Since we have still 2 minutes is to, and so maybe I can stop here.
Questions? I have one naive question. Is this more a result about splitting the normal bundle or about lifting bundle? I mean, what is your opinion?
These conditions, so if the extension exists, then the splitting bundle considered splits. But in general, it's, I don't think it holds in general. Because in all this, in the proof of the first result, I make repeated application of the fact of the hypothesis that X was small codimension in the same sign wave. But say philosophically, proving these theorems was for me a sort of attraction because I can confess that I like very much the proof of the result proved by British Harris Tulek and the proof given by Ellingfield, Lucian Badescu, and Strömmer. I repeat, that extension to the first infinitesimal neighborhood, the existence of that extension in that case was crucial. It doesn't necessarily follow that then we have the extension in general, but we have to work a little bit for it. And the other step was not at all trivial.
One more question? Thank you once more. We have exactly 10 minutes.
Why not? What about that? That's the interpretation.
We have some subwriting with
Maybe you should ask Hartson, but now this question is such kind of questions as far as I understood. Because